Hi everyone, this video is about revision of the exponential function topic that you would have studied earlier in the year. So we're looking at this document here, which you should have downloaded. You can see on the syllabus document the first things that you would have covered on exponentials and logarithms. That's all of this stuff down here. Developing the use of index laws, establishing the use and properties of exponential functions, drawing their graphs. This is an important one, understanding the relationship between exponential functions and logarithmic functions, and properties of log functions, drawing graphs, using laws of logarithms, and practical growth and decay problems. So I'm going to go through just a few of these examples on this one here and want you to try and do a few as well. So let's have a look at the first question here. We've got a grasshopper plague. And the area affected by the grasshoppers is given by that equation there, 1000 times 2 to the 0.2 n, where n is the number of weeks after the initial observation. Find the original affected area. So when they say original, they mean when t equals 0, or in this case, n equals 0. So we substitute n equals 0 into there, 0.2 times 0, 2 to the 0, anything to the power of 0 is 1. So that gives us 1000 grasshoppers initially. The next question, finding the affected area after 5 and 10 weeks, we use the same equation, just substitute in 5 and 10. Find the affected area after 12 weeks, same thing, and then draw the graph. Let me look at, show you the answers, which you need to see for this one here. So the first one's 1000. If we substitute in that one after 5 weeks, we get 2000 hectares. After 10 weeks, we get 4,000 hectares. After 12 weeks, using our calculator, we get approximately 5,278, or about 5,300 hectares. Here's what the graph looks like. So this exponential growth here, as you can see. So have a go at the next question here about the CD player, a very similar question, and write your answers here. Okay, we need to understand this relationship here between exponential functions, in this case y equals or 10 to the power of x, and the inverse function, which is the logarithm function. Okay, an inverse function is just a reflection in the line y equals x. That's the graphical interpretation of what an inverse function does. Okay, so 1, 0 is, or 0, 1 is on the original curve, so 1, 0 is on the inverse. If the 0.14 was, 110 would be on this graph here, x equals 1, y equals 10, then the 0.10, 1 will be on the inverse function. So you just swap around the coordinates if you want to do that to get an idea of the graph. Okay, so what are logarithms? It's sometimes a tricky thing that people don't really get and don't try, kind of find hard to understand what a logarithm is. So let me try and give you a little bit of an explanation of the way that I think about logarithms. So if you've got your normal number line that we're used to dealing with, and here it is here, starting at 0, 1, 2, 3, 4. Now this is just a bit of a sketch here. And I'm going to look at a number line here, and let's say 2 to the power of 0 is 1. 2 to the power of 1 is equal to 2. 2 to the power of 2 is 4. And 2 to the power of 3 is 8. Okay, now imagine that second number line there. I said, right, this is going to be the base 2 number line. So I really don't need to know anything about these 2's anymore. I know that each one of these numbers has a base of 2. There you have a logarithmic scale, or some logarithms. They're just numbers written with different bases. That's all they are. So instead of writing 8 as the number 8, with a base of 2, the number 8 is 2 cubed. Well, with the base of 2, it's 3. So we'd say the logarithm with a base of 2 of the number 8 is equal to 3. That's the logarithm statement. So it's just a number written with a different base. Let's do the same thing. Let's say that we take a number line here, and this is my base 3 number line. Notice 3 to the power of 0 is 1. 3 to the power of 1 is 3. And 3 to the power of 2 is 9, right? So again, if I know this is my base 3 number line, I'll just get rid of those 3's, and there's my logarithmic scale there for base 3. Now I could say the logarithm on the base 3 number line of the number 9 is 2. That makes sense? What about if I said the logarithm of the base 3 of the number 5? Well, that is this number right here. So I'm saying, well, that looks like around about 1.3 to me, approximately. Okay, that's how it works. So logarithms are just numbers with different bases. I hope that's not too confusing. If we have a look at some examples on here now, guys. Write an equivalent exponential statement for log base 10 1000 equals 3. So for part A, you would write 10 to the power of 3 equals 1000. Okay, can you write your answer for part B now? In this page here, log base 10 of 100. So let's say log base 10, 100 equals x. That's what we want to know. So converting that to an index statement, 10 to the power of x equals 100. And then we can clearly see that x is equal to 2. Can you write your answer to part B and C now? Laws of logarithms. You should have these written down, what the laws of logarithms are. So let me just do A. One of the log laws we know is that log A plus log B is log AB. So log 5 plus log 3 is just log 5 times 3, log 15. Part B, we know log A minus log B is just log A over B. So log 24 over 8, so log 3. Write down your answer to part C now. In writing this one as a single logarithm, 2 log 7, we know that log rule that says 2 log 7 is the same as log 7 squared. 3 log 2 would be the same as log 2 cubed. So we've got log 49 minus log 8. And writing that as a single logarithm, log of 49 over 8. Okay, can you write your answer to part B now? Okay, flicking over to page 15 now. Write the following as logarithmic equations, so with logarithms in there. So if I take the log of both sides, I get log of y equals log of a squared b. Log y equals, the log law that we know is log AB is log A plus log B. So I can separate them out like that, and I know a little bit about that rule that says log A squared would be the same as 2 log A plus log B. There we go. So I've written this out as logarithmic equations. Can you give me your answer to part B now? Last one. Write the following equations without logarithms. Okay. We've got log A equals log B plus log C squared. Cool. That's just putting that 2 and putting it there to the top. So on the right hand side, that gives us log BC squared. Cool. Now that we've just got log of this equals log of this, clearly A must be the same as BC squared. Great. Can you give your answer to part B? Last one is this function here. F of x is log base 2 x minus 1 plus 1. Let's have a look at the answer to that one, to that question. Okay, last question here. We've got a function f of x log base 2 x minus 1 plus 1. So we just need to understand a little bit about what the movement is going on here, the domain and range, etc. Well, for the domain, what possible x values can we have? We know that logarithms can't be negative. We can't have log base 2 of even 0. That doesn't make sense. 2 to the power of something equals 0 does not make sense. We can't have a negative number here. So I know that this number here must be positive. X minus 1 has got to be greater than 0. So x has got to be greater than 1. The range also, it really helps actually just to sketch the graph here, have a look at the graph, and then it helps us to kind of go back and think of what the domain and range is going to be. So let's look at the graph of that function, and we can fill in the answers. Here it is, log base 2 x minus 1. So the x minus 1 means we've shifted everything across 1. So now the y-axis is not the asymptote here, it's the line x equals 1 that the curve's getting closer to. Plus 1 means we've shifted everything up 1. So rather than going through 0, 1, it's shifted up 1. So here it's going through the point 2, 1. A significant point on there is if you put 5 in there, 5 minus 1 is 4, log base 2 of 4 is 2, plus 1 is 3. So there's the curve there. We can see that our domain, the possible x values, are x values greater than 1. The range is any value. We're going right down to negative infinity there. We're going right up to positive infinity, though at a slow rate, but we will get there eventually. The x-intercept here is when y is equal to 0. So you can see, solving that equation, y equals 0, we get this. X minus 1 is 2 to the power of minus 1, which gives us x is 1.5. So the x-intercept is 1.5. Sketching this graph will obviously be really easy to do it on Desmos or a graphing calculator, so you can see those important features as well. Last question says find the inverse function. Let's look at this. So if this is the original function, the inverse is where we just swap the x and the y values, and that's what we've done at this step right here. Swap the x and the y values. I've then got to rearrange this to get y on its own. So subtract 1 from both sides. 2 to the power of both sides gives us this. 2 to the power of x minus 1. 2 to the power of log base 2 y minus 1 just leaves us with y minus 1. And then we add 1 to both sides. There is our inverse function. Now if you drew that inverse function, you'd see it would just be a reflection in the line y equals x, this one here. And that's your last thing. It's just to have a draw of this function, the original function, and this one here just to confirm that fact.